It's my pleasure to introduce Dr. Tim McCoy, who's the National Curator of Meteorites at the Smithsonian Institution in Washington, D.C. A little bit about Tim. So Tim did his bachelor's, master's, and doctoral degrees from, respectively, Eastern Illinois University, the University of New Mexico, and the University of Hawaii. I don't have dates, but I just asked him, and Tim said 18 something was when you did your first degree. Okay, so Tim has obviously defied the aging process and is immortal in some fashion. So congrats to Tim. Tim's postdoc was at NASA Johnson Space Center in experimental metrology. Then he moved to the Smithsonian, where he has been for the past 28 years. Tim has curated the National Meteorite Collection. He has classified more than 10,000 Antarctic meteorites. He helped finish the Geology, Gems, and Mineral Hall. He served twice as chair of the Department of Mineral Sciences. For that alone, he deserves a round of applause, I think. He has worked on 6 robotic spacecraft missions near, is it Mir? Dawn, Messenger, OSIRIS-REx, and Psyche, which is on its way. He is a citizen of the Miami tribe of Oklahoma and a learner and teacher of their language and culture. He is a borderline obsessive geocacher. And if you don't know what geocaching is, you can ask Tim all about it. I've been regaled with stories of geocaching before all kinds of OREX meetings. Tim is up at like 4 a.m, beating the heat in the summer to do geocaching and things like that. Tim has a very long history with the University of Arizona. When Mike Drake, our late LPL director, visited the University of Hawaii for a month or two, when he was working with Tim's PhD advisor, the late Professor Klaus Keil, which those of you who have been in cosmochemistry for some time know those names very well. Tim also worked with our own Bill Boynton on the NEAR mission. He's been a collaborator with Professor Dante Loretta, for many years. He was a committee member and later postdoc advisor for LPL alum Kat Gardner-Vandy, with whom he still collaborates. He's an informal mentor for our own Sam Crossley, now here at LPL with us. And Zoe Wilbur, former graduate student with Professor Jessica Barnes, is now a postdoc with Tim at the Smithsonian. And for the past 6 years, Tim has been a partner with me in leading the mineralogy and petrology group on OSIRIS-REx, and he's been the deputy mission sample scientist as well. Tim has been a friend and a collaborator for many years, and I am very pleased to welcome you today to give our departmental seminars. So welcome to Tim.
Grad students for sitting and representing a close packed sphere group right up there in the center. So one of the humbling things about working in a museum is no matter how important you think your work is, some little 8-year-old kid's going to go, so what? And so I'm going to start with the so what. I think, I've worked on 6 missions. I've looked at thousands of spacecraft images among the billions we've taken. But arguably, this is the most important image ever taken. It was taken Christmas Eve, 1968 by the crew of Apollo 8. And it's Earthrise. It's the first time that the Earth was really observed rising above the surface of the moon. And it really brought out 3 unique features of our planet: that it has water-rich oceans, that it has abundant life, and it has silica-rich continents that rise above those oceans. And those 3 features make our planet unique. And they also must be interrelated. We know enough about each one to know that each one is dependent on the others. And so at the Smithsonian, OSIRIS-REx is part of a larger project that we call Our Unique Planet to really understand these 3 features. And so, of course, I work on OSIRIS-REx down here. This is my former postdoc, Nicole Lunning, who's now the curator of the OSIRIS-REx samples at JSC. This is my colleague, Mike Ackerson, his postdoc, Riju Chowdhury. This is at the Acosta Gneiss. They're actually standing on the oldest rocks in North America. And my colleague, Yon Laskew, and his postdoc, Sejad Akam, and they're studying the rise of magnetotactic bacteria, looking at cores across the Great Oxidation Event from about 2.2 billion years ago. And so each of these projects is really feeding into this overall mission. And of course, a big part of this was OSIRIS-REx, which I've worked on now for 21 years, amazingly, back to when it was the original OSIRIS proposal, through 2 rounds of proposals as OSIRIS, through the creation of the New Frontiers program, and ultimately the proposal that became OSIRIS-REx, the selection, the build, launch, proximity operations. I had a postdoc, Erica Jawan, who did much of the geologic mapping, and ultimately the sample return with this parachute, which those of you that were watching that knew what was going on, I have never been happier to see a parachute in my life, keeping in mind that I do not skydive. And so in many ways, most people probably looked at this and said, this is the end of the OSIRIS-REx mission. And for us, it was really just beginning at the Smithsonian. And so within 6 weeks of the sample returning to Earth, we opened an exhibit, a single case within our Geology, Gems, and Minerals Hall, a view of the beginning, which it both is at the temporal beginning of the hall, the place where the birth of the solar system is discussed, and really at the physical beginning of there. And we put on exhibit the first specimen of Bennu that was available anywhere in the world. And it's not a particularly impressive specimen. I think it's 136 milligrams that we encased in here, but really contextualizing it within this larger question of, could this fragment of an asteroid hold information about the beginnings of our solar system and the formation of life on Earth? That's the question we asked 6 weeks into this mission. But we couldn't have really imagined where that journey was going to take us. And that journey has taken us from an SEM lab through 20 team borax. If any of you use detergent, 20 team borax, we'll show you that, to the E ring of Saturn, and ultimately to RNA. So let's get started on our journey. It ended up with this paper. If you too study Bennu samples, you can get the cover of Nature. You and 64 of your closest friends, or 65 of your closest friends here. Here's the whole co-author list. Many of them are in this room today. And it came out January 29th with a companion paper in Nature Astronomy that was led by Jason Dworkin and Danny Glavin at Goddard Space Flight Center on announcing the organics in here. And these were really large multinational projects. To give you a sense of the scope, there were people in 1, 2, 3, 4, 5, 6, 7 countries, I think, working across 4 continents. I think there were 9 states represented in the United States. And so this group of 66 people, just for the Evaporite part, worked across these continents, looking at hundreds of samples to put together this story. But at the Smithsonian, it was really 5 of us that were the core. And these are the 5. This is our new scanning electron microscope lab that we built with money that was given by donors specifically to buy this instrument to study Bennu samples. So this is a field emission gun SEM. And the thing that makes it so unusual is it has 2 EDS spectrometers opposed from each other, so that when we look at rough samples, we don't get the kind of shadowing that you normally get in here. The group, this is Tim Rose. He's our lab manager. He has 45 years of federal service working on microbeam instrumentation. Myself, Rob Wardell, Carrie Corrigan. Many of you know Carrie in the back, one of our meteorite curators, an expert, among other things, at CM chondrites, has worked on the porosity of CM chondrites. And Tim Gooding, who's one of our sample preparators, who made some of the sections that you'll see in a minute. And we have a very particular way we like to work at the Smithsonian, and it's methodical, it's slow, but we like it. And so we start with something like this. Is a Keon's image taken here at the University of Arizona. This is 803.103, which is a aggregate particle. These are basically millimeter-sized particles. And we will go in and we'll take one particle, say this one, a hummocky particle, and we'll pick it out, and we mount it on a parafilm, not on carbon tape. We found carbon tape was too sticky. So we take a piece of parafilm, we iridium coat the parafilm rather than carbon coat. We put the piece down, we then iridium coat that. You'll see why the iridium coating is important in a little bit. And we study the entire exposed surface here as much as possible. Once we do that, and only after we do that, do we then decide how we want to orient it to make sections. And we will take this and cut it in half and bookend it and make two sections, opposing sections of this piece. So this is all different ways of viewing the exact same piece. And we had been working on this. We started, I was on the quick look team as soon as the samples came back down at Johnson Space Center, and we began working shortly thereafter at the museum and seeing a lot of the same things that everybody else was seeing. So just to give you a perspective, this is a sulfide crystal in Bennu. You can see the scale. I had never really worked on CI chondrites or CI-like chondrite type things in any detail. I work on iron meteorites for the most part, on igneous rocks. I worry mostly about the differentiation of planetary bodies in the early history of the solar system. So to suddenly be faced with a rock where everything is, a micron, 2 microns, 5 microns is a huge grain, is really a daunting task. It's really an overwhelming task to try to go through here. And you see these just marvelous shapes within here, all set within this sheet silicate, phyllosilicate matrix with little, magnetite framboids mixed in here. And you're just picking through this rock, these micron-sized grains in a single millimeter-sized particle. I don't know, there must be tens of thousands of grains within here. And you see every different form of this. This happens to be a bug. And so you can see it sort of has a euhedral shape up here. This is an apatite grain. You have this sort of fibrous, magnesium-rich phyllosilicate in here. In this part, in the phyllosilicates, you can see lots and lots of sulfides scattered everywhere. This is this compact, early formed phyllosilicate. But this sort of fluffy, magnesium-rich stuff has very little sulfide in it. And then you have these, what we called chopsticks for a long time. These are two plates of sulfide that grow within these vugs. We found these now in 3 dimensions. And so again, same thing a lot of people had seen. We keep going. We called these eggs early on. Fortunately, none of them hatched with little, Bennulings coming out of them. Again, tiny little things, a few microns in size. And we stared at these quite a while because they looked so familiar, but we couldn't quite place it. And what I think they are is little dogtooth spars. So this is a calcite called a dogtooth spar on Earth. And I think these are little short, squat, sort of imperfect scalenihedra that you see in here. And, these calcites are very pure. They have relatively little iron, magnesium, manganese in here. You can see it here, these calcites plot way up here. But there are 2 other phases. We have a dolomite that's sort of 50-50 calcium, magnesium. And then we have magnesite. Those of you that are into minerals, some people like to call it brunerite. That's been discredited by the International Mineralogical Association. And you can see that has a fair amount of iron and especially manganese. Some of these have, 7, 8, 8% manganese within them. Magnetites, we've seen lots and lots of magnetites. Kathy Thomas Kepperta at JSC has probably taken 1 billion photos of magnetite by now, and I pity Pierre when she goes to put them all in Sammy's, but it will be coming. And, you get every form in here. Oftentimes you get these sort of, cuboctahedral shapes. You get a few cubic shapes. You get all sorts of different things in here. And these are just the small ones. You also get, plaquettes. You get every different form in here. And sometimes we can begin to see the relationships if we look at this. This is an image out of the Natural History Museum, which Jess actually put me on to. And here we have calcites, and these are the little framboid magnetites. This is phosphate. We'll get to that in a little bit. But you can see how the magnetites enclose the calcites. And so we start to see some petrogenetic, some order of formation in here. The calcites obviously had to exist before the magnetites formed, and then both of those existed before the phosphate formed. And this is the kind of just basic spatial relationships that geologists do every day. And then sometimes we see more complex intergrowth. So, for example, this is from Guy Liberel at Nice, and this is a cathodoluminescence image. This magnesite, the magnesium carbonate, which doesn't fluoresce in here, inside coexisting with dolomite, and then enclosed in a dolomite-rich rim. So that kind of suggests magnesite and dolomite probably co-precipitated, co-formed at some point, maybe with a longer period of growth or second period of growth of dolomite in here. And you can start again to see these relationships. So for example, here's just an X-ray map, and we see magnetite, the red, enclosed in this green teal dolomite. And so the dolomite actually obviously formed after the magnetite. So now we have calcite, magnetite, and then dolomite and magnesite probably together. And again, we see this magnesium sodium phosphate rimming the dolomite. So it had to come after the dolomite, and often intergrown with this intensely blue phase that you see in here, which is that same sort of fibrous, sulfur-free, magnesium-rich phyllosilicate. Those two are oftentimes go hand in hand in these rocks. And that magnesium sodium phosphate is something we saw literally the first day we began to look at the samples. When we were handed the quick look samples at JSC, one of the first things we saw was this funny shaped, weird little white grain of magnesium phosphate. I fully admit I thought it was a contaminant. It turned out not to be, but it forms on these rocks, oftentimes on these fracture surfaces, and these are given the name the mottled lithology, just because they have this black and white sort of salt and pepper mottled shape in here. And if we take this exact piece and we look in here and we put this in the SEM, we see this. We call this phosphate cliff. It's only about 100 microns high, so if you fall off of it, nothing actually bad is going to happen to you. And it's this magnesium sodium phosphate. It's very cracked looking. You can see it forms an obvious sort of layer on here, an obvious coating on these surfaces. In some places, we can find it where it's actually cracks in here. So this is where the rock broke. The magnesium sodium phosphate was more fragile. That exposed it to the surface. And probably long before that exposure of the rock we call this thing today, this was all desiccated. So this is a hydrous phase. It still is quite hydrous. Some of the spectroscopists think it could have up to 28% water in it. And yet it's been desiccated. And structurally, it's amorphous. This is work from our colleague Ashley King at the Natural History Museum. He separated one of these little pieces, that's it in the SEM, put it in a loop, did an X-ray diffraction. You can see there's no real peaks there. And so this is an amorphous magnesium sodium phosphate. It's something we've never seen in a meteorite sample. We've never seen it on Earth. We've never seen this stuff before. It's really a new, it's not a mineral, it's a new phase in our lexicon of understanding these. And Tom and I just yesterday confirmed there's at least a second of these hydrated amorphous phases. We determined that the aluminum hydroxide that I'd found is in fact amorphous and almost certainly hydrous. And so something is going on in this asteroid to form these hydrous phases, and then in some cases they dehydrate, they fracture like this. And so life was good. We're going along. We think we understand the sample. There's this weird magnesium sodium phosphate. Dante's convinced it's due to fluid mobility, which kind of makes sense. It has a lot of fluid mobile elements in it. He writes his paper. Life is good. And then we decided to pick out this sample right here. Now, we'd had our eye on this sample for a while because it has these funny white veins in here. Now, by this point, if you had asked me, if you'd asked almost anyone, you see white veins, that's magnesium sodium phosphate. White stuff, magnesium sodium phosphate. In fact, we were so sure of that we didn't even do this as the first one. We saved it to the fourth out of this, the 10th we had done overall. And when we looked at it, well, it turned out to be something completely different. It was these. Thousands of tiny little needles, only about a micron wide, 5 to 10 microns long, and they occur in these cracks. In fact, if I go back, what they probably are is not really even veins. They're probably under a sheet that underlies this clast-like structure, which is hard to tell from here, but it's quite flat. And I suspect if you were to pop that off, you would find an entire sheet of this material underlying that. And I'll show you an example in a little bit. So this is the first spectra we ever took of this stuff. And you can see it's oxygen and sodium and carbon. There's a little bit of magnesium, a little bit of silicon, a little bit of phosphorus. And it took us a little while to wrap our brain around this. Like, what is this stuff? We'd never seen this in a meteorite. Like, I've been studying meteorites for 40 years. I've literally, as Tom said, I've looked at 10,000 meteorites. I've never seen this stuff. And so it took us a while to realize, first of all, that the carbon peak was real. And we know that because we have a coater that allows us to coat with iridium. And so when we see carbon in the sample, we know that it's real carbon. It's not from the carbon coat. So we thought, well, maybe it's a sodium oxide or sodium hydroxide, which you know is Drano. And this led Tim Gooding to a whole, he has a whole theory about that, this is the further proof of the alien civilization that had their spacecraft and their toilets were clogged and they had to use Drano, but that's a separate story. And ultimately we came to the conclusion it was, in fact, sodium carbonate. We ended up confirming this, came back out here to Arizona, worked with Tom, separated a fib section, did some mapping of this. You can see sodium, carbon, oxygen in here, did the pattern on it. And it's not a great pattern. It's probably not perfectly crystalline, but we were able to index this to only 3 phases were even possible: Noccolite, Trona, and Vegscheiderite. Vegscheiderite's a very obscure phase. It was actually discovered by someone at the Smithsonian. But almost certainly Trona is the most likely candidate. Now, a lot of other places, like if you were at the University of Arizona and you were a graduate student, you found this, you'd probably go dig through the literature and say, hey, what do I know about sodium carbonates? That's not really what we do at the Smithsonian. We go down to the mineral collection and we say, hey, do you have any terrestrial sodium carbonates we can look at? And the collection manager, he loves showing you weird stuff, like anything that people haven't looked at in 10 years. He loves opening the drawers. So we go and we open this drawer. And the first sample I noticed was this one. You can see this is a centimeter cube. This is from Lake Magadi in Kenya. It's a soda lake, a carbonate-rich lake, and it is sodium carbonate. This is another view of those sodium carbonate needles in Bennu. And yes, these are 1,000 times bigger than these, but it is the same habit of the same mineral. And so whatever formed this probably formed those. And that's the path we went down. And the place we wound, this is another example. This is actually from the place we went to. This is from Searles Lake in California. And this, even more than the specimen, this label, Searles Lake, San Bernardino County, California, is what led us to Searles Lake. Now, you've probably never heard of Searles Lake, but if you go to California, down here, sort of, this part of California, and you find the Long Valley caldera, this big Yellowstone-like collapsed caldera, there's a river that flows out of there. It's called the Owens River, and it feeds the Owens Lake. Now, Owens Lake used to feed 4 other lakes. China Lake would overflow to Searles Lake, would overflow to Paramount Lake, and ultimately overflow to Lake Manly, which is Death Valley National Park. These were hundreds of meters deep in water, and they evaporated. And when they evaporated, they formed a whole sequence of minerals in here. Now, you may not know any of these minerals, but you know this place because this is where 20 mule team borax was born. This is where borax was mined in Searles Lake and Death Valley. And 20 mules, 2 horses, 2 wagons of borax, and a water barrel were hooked together to make the roughly 100-mile trip from Death Valley or Searles Lake to the railhead in Mojave, where it was taken not to do your detergent, although it does a nice job cleaning your clothes, but actually it was used to refine gold during the gold rush in California. And so 20 mule team borax was born of Searles Lake. And we can also understand this conceptually. We don't just have an example of this, we actually have a pathway. So this was some work that was built on of a study by Hardy and Oikster in 1970. So this is a 55-year-old conceptual idea that if you take dilute solutions with sodium, calcium, magnesium, bicarbonate, sulfate, chlorine, and you go down these various paths. So if calcite crystallizes first, right, then you can go down a variety of different paths. But if you go from calcite down to magnesium calcite, dolomite, or magnesite. This essentially takes the calcium out of the system, this set of crystallization. And that will lead you down a path where alkalis are more than 2 times calcium plus magnesium. And that brings you to Searles Lake, where you're high in sodium, carbonate, sulfate, and chlorine. So because we had, as I showed you, the early crystallization of carbonates, because we had a carbonate-rich system, we eventually evolved to where we get a sodium carbonate-rich system. And this was all described in a very nice paper by Christian Olsen and Tim Lowenstein from SUNY Binghamton. And in the small world category, it turns out I haven't talked to him in 25 years. I sent him an email recently, but I actually know Tim Lowenstein because 25 years ago, I had an intern at the museum. We have an intern program. I had an intern who came from SUNY Binghamton. She invited me to come up and give a colloquium, the only time an undergrad had ever invited someone up to give a colloquium there. And I stayed, my wife and I stayed at the home of a young professor named Tim Lowenstein. Our paths went completely different directions for the next quarter of a century, and came back together in understanding sodium carbonate evaporites. And again, this group developed an entire sequence in here: calcite, aragonite, dolomite, galasite, personite, northopite, borax. Now, we're not going to see borax on Bennu because there's not enough boron. And essentially, the sodium magnesium phosphate substitutes for the sodium boron phase, borax. You see nacolite and phenardite and trona and halite. This essentially became a cheat code. This allowed us to figure out what we were looking for. This was the connective tissue that allowed us to realize we were looking at a mineral sequence in here. And further, it allowed us to say, what hadn't we found? And that's when we started reaching out to the entire team and saying, has anyone seen any of these things? In fact, they had, and they didn't, in some cases, didn't realize what they were looking at. So maybe one of the most interesting ones, I think, is these tiny little grains. This is TEM work by Sherry Singerling and Frank Brenkern in Germany. And this is either galasite or personite, hydrated calcium sodium carbonate. You can see it's only 200 nanometers in scale. These are single grains. I wish we actually had more of these because this has a really interesting history. At Searles Lake, this formed by syn depositional back reaction. So essentially, calcium carbonates react with the sodium fluid to make the sodium calcium carbonate. We don't know whether that happened here because we don't have any petrographic relationship in these crushed grains that were studied by TEM. We have rare grains of phenardite, which is the sodium sulfate. These are found by Kathy Thomas Kepperta at JSC. The Australian group, Nick Timms and others, had found halite and sylvite in these rocks, which is really interesting. So the sodium chloride and the potassium chloride. If any of you are old enough to remember when salt substitutes were incredibly bitter, that's because they were potassium chloride. And Kathy had even found these very rare sort of micron-sized grains of sodium fluoride. We call this a Williamite on Earth. It's a beautiful red grain. You can get some samples out of Russia. I'm sure they sell them at the Tucson Gem and Mineral Show. It also dissolves in water. And so really interesting. And so we were able to put together an entire mineral sequence here and to understand how this evolved. And so this is just the order of the phases. We have a rough idea of the fluid composition, the major control on the phases, what went in, what went out of the system. And then these are the things. So you start with the carbonates. You have calcium, magnesium, calcium, sodium carbonate. So these are your carbonates. Then you have a magnesium, sodium phosphate. And then you have a whole bunch of sodium-rich phases with a potassium phase thrown in here. And what you're really looking at is the evolution from a neutral solution where sodium plus potassium is probably less than 2 times calcium plus magnesium, but you're increasing the alkalinity, probably by evaporation. And we can estimate the amount of evaporation by taking, a rough estimate of the bulk chlorine, calculating what the bulk salinity would have been, knowing the water rock ratio. And these are rough estimates. So these are sort of minimums, probably higher than this. But to get out here to Williamite, you're looking at something like at least 70% evaporation, probably higher than that. And eventually, you get to the point where you get an alkaline fluid. And here, you're probably dominated more by water rock reactions that form the carbonates. here, evaporation is really, it's driving the bus. That's what's going on there. And several of these phases, if we look at like galicite, personite, we saw these in the samples, right? So we actually saw the galicite, personite, phenardite, trona, halite, calcite. But many of these, let me just back up one, many of these, particularly the calcium sodium carbonate, the magnesium sodium phosphate, the sodium sulfate, the sodium carbonate, potassium chloride, and the sodium fluoride, had never been seen in a meteorite before. Never. No one had ever reported these. There were a few rare reports of salt, of halite, of sodium chloride. So why? Why were these not there? The answer is because of how they were stored. So we were given directions on the mission to store these in nitrogen, but it was really a best effort, what you could do. We happen to have 2 Tims and a Rob and 50 years of junk sitting around. And so they took these old desiccators and they retrofit them for nitrogen. We flow high rates of nitrogen through here. Many, fractions of a cubic foot per minute in here to flush the system. And ultimately, we have a check valve over here, so we don't have to flow constantly. And we can achieve a relative humidity. This is the latest reading. Typically, that's 1%. That's very typical for us, and it's probably a maximum in here. We get very typical things, but not everyone had this ability. Not everyone really got the memo that they were supposed to store them this way. And unfortunately, 3 of these phases were lost. That which comes from water will go back to water. And so the calcium sodium carbonate imaged about 8 months after the original. It was growing sodium chloride grains, and the structure of it had fundamentally changed. And when Nick Timms went back to look at the halite and sylvite, all he found were holes. They were gone. Didn't surprise me, shocked him. These were at 30 to 40% relative humidity. This was probably 10 to 20% relative humidity, which is vanishingly small. That's what we store meteorites at in just desiccator cabinets. But it was too much for these samples. And so they really are an incredibly precious thing. And they tell us a great deal about the solution. So let's just look at a couple of the things they tell us. One of which is the temperature of that solution. Remember, I showed you those sulfides very on. This is a ternary iron plus cobalt, nickel, and sulfur. This is from an upcoming paper by Zaga and McCoy. Tickets become available on Friday. You'll want to get yours early because I'm sure the theater will sell out. But this is a 25 degrees C isothermal diagram. There's some uncertainty in this, but basically the best fit to this data between pyrrhotite and pentlandite is something like 25 degrees C. So I think if you'd ask people, well, what's the temperature of these fluids? You might have gotten all kinds of answers. But at this point, this is sort of tepid water, right? And we can see this in other examples. Sometimes we don't have a thermometer per se, but we have a stability. So this is the stability phase diagram depending on the partial pressure of CO2 for trona. And you can see, depending on the temperature and the partial pressure, but trona, which is this field, can only form at temperatures if it were, say, 1 atmosphere or 1, microatmosphere here. This is 1,000 mic, 1 atmosphere. Yeah, this is basically 20 degrees C. So trona has to be above 20 degrees C. We have other thermometers I'm not going to show you, but we're consistently getting temperatures of about 20 to 25 degrees C. Tepid, salty water on the surface of Bennu. Now, what's really remarkable is that these same minerals we see elsewhere in the solar system. This is the dwarf planet Ceres. Everyone knows, at least where I work, everyone knows that Pluto was downgraded from a planet to a dwarf planet. They're all still very upset about it. But at the same time, Ceres was upgraded from an asteroid to a dwarf planet. It's the largest object in the asteroid belt. And this is Akator crater. It's about 92 kilometers across. It's only about 20 million years old. And in the middle is this white deposit. Spectroscopically, that's sodium carbonate. Now, if you'd asked me, what does this look like at fine scale? If you had told me that it was going to be trillions of tiny little needles, maybe a micron wide and 5 to 10 microns long, I would have said you're crazy. But that's quite likely what this material is, formed from a recent brine geologically recent brine, almost a modern brine, under the surface of Ceres. Even more recently, the E-ring of Saturn here is formed by the plumes of Enceladus. Cassini flew through the E-rings of Saturn and measured both sodium carbonate and sodium phosphate. And so the same minerals that we see in this fossil brine 4.5 billion years ago on Bennu are forming today in the icy outer planets of our solar system, the moons and satellites of our solar system. And that's a remarkable, remarkable thing. And on Bennu, these didn't form in a subsurface ocean or a surface ocean. They probably formed in relatively small cracks of water beneath the surface. This is a rock from the surface of Bennu. This is work by Hannah Kaplan, who observed these carbonate-rich veins. They're only about 10 centimeters wide, half a meter long, and they're mostly carbonate, as you would expect, because in the evaporite sequence, most of what you get is carbonate. But that carbonate is the perfect environment for this evaporation, for this fluid evolution to take place in relatively small bodies of water under the surface of this asteroid, its parent asteroid, the mud ball that it formed from 4.5 billion years ago. Now, if you know anything about this study at all, so far I've given you a lot of mineralogy and a lot of geology, but that's not what got all the press. What got the press was life. So I'm going to walk you through that part. This is a image I like from Lanier and Williams. So I work primarily in a biology museum. I'm surrounded by biologists all the time. Biologists love these trees of life. These are the 3 domains of life. Basically everything you know or like, if you're a bird watcher, mammals, invertebrates, doesn't really matter, probably lives on the tip of this little bit right up here. And that's evolved in the last, tens of millions of years. But if you follow this tree of life back far enough, you get to Luca, the last universal common ancestor. Now, where did Luca come from? Where did the last universal common ancestor come from? Well, we know something about life. We know life requires 3 things. It requires energy, it requires information, and it requires compartmentalization. We don't know which of these came first, but of all the theories of life, the origin of life, you can really divide them into which of these is the preferred characteristic. Which one came first? Was it the metabolism first world, the one that produced energy? Was it the membrane world, a thermal vent world, a place that would have energy? Clays, which can do both energy and compartmentalization. But one of the most popular is the RNA world. The idea that the development of RNA, the single strand cousin of DNA, was really the first step to life. So that's simple. We just make some RNA, right? But let's talk about how complicated that really is. You're talking about taking 5 simple elements: carbon, hydrogen, oxygen, nitrogen, phosphorus. And you're talking about making that. This is DNA. RNA is its single strand cousin. Now, I don't know much about RNA, but it turns out that what you have are nitrogenous bases or nucleobases in DNA. In RNA, you only have one of these. But this whole thing that we think of as the spiral is really a combination of sugar and phosphate. And this molecule is so complex, it almost shouldn't exist. To give you an idea, there are almost as many atoms in a single strand of DNA as there are stars in the Milky Way galaxy. How in the world are you going to take these 5 things and make that thing? Well, you're not, because that's not what you have to do. You don't have to make the whole thing. You just have to make one rung of the ladder, right? This is one rung of RNA. It's just a phosphate, a sugar, in this case, a 5-carbon sugar, ribose, and a nucleobase. This happens to be adenine. You probably know about the 5 essential nucleobases for life. So let's see if we can actually do this. So we're going to try to take carbon, hydrogen, oxygen, nitrogen, and phosphorus. And we're just going to see if we can make those 3 things, right? You got to make 3 things to make one rung of the ladder. Well, we need the nucleobases. They're adenine, guanine, thymine, cytosine, and uracil. Uracil is the one used in RNA. If I remember right, cytosine is the one used in DNA, and the other 3 are used in both. We have all 5 of these in the samples. That was the work that Jason and Danny published. Exceptional work showing that all 5 bioessential nucleobases exist in these samples. We're looking for ribose, for the 5-carbon sugar. We've seen it in meteorites before. We expect to see it in the samples. But more importantly, we think we know how it forms. So for example, if you take formaldehyde, which we have in the samples, and hydroxyapatite, which we have in the samples, there's work showing you can form ribose. So we don't, not just finding the ribose, but finding the mineral that templated that ribose. The basic building block that allowed us to make the ribose. And finally, you need a phosphate. Now, this sounds easy. We know we have phosphates in here. But the problem has been, how do you keep the phosphates in solution? Phosphates love calcium. They love, love, love calcium. And so they'll almost always bind with calcium. And then calcium phosphate's not soluble in the fluid. So how do you keep it in there? Well, you keep it in there by following these geochemical pathways of Hardy and Oyster. And then Toner and Catling in 2019 really promoted this, that by having calcite, magnesite, dolomite precipitation, you can make the alkalis exceed calcium, and that's how you get to Searles Lake brine. So only in a Searles Lake kind of brine can you keep phosphate in there and ultimately make something like a magnesium phosphate or a sodium phosphate. So we have the building blocks of RNA. Did we make an RNA? Or did we make a nucleotide? Just, one of these 3 pieces put together? We don't know. We haven't measured one. And keep in mind that it's a difficult measurement, right? And the beauty of it is we have the sample here on Earth. It's well preserved. We don't have to make the measurement. We don't have to decide we want to sacrifice as much material. And every time we go to one of these steps, you would expect you'd make less and less and less of it. And one of the reasons you might think is because these are actually catalyzed by salts, which we have a lot of. Did we make a full string RNA? Well, we don't know. But these are catalyzed by clays. Now, in this case, most of the clays that have been catalyzed on are dioctahedral smectites. So things like montmorillonite, where you have aluminum. We have trioctahedral smectites that are magnesium dominated. But we could do the experiments and actually figure out if those are capable. And again, once you pile these on, you make these nucleotides, and you need probably 50 of these to become a stable structure. So you're piling them on. They bind tighter and tighter and tighter. At some point, you need to release them from that clay. That's what salt solutions do for you. So we have the building blocks. Did we go there? Well, I think it's like making cookies. I can give you the ingredients. You can make the dough. That doesn't give you a cookie, as Tom well knows, because my wife makes cookies for Tom every time we come and visit. And, you have to add some heat and some time. So we don't know. But what we can say confidently is that we have not just the precursor molecules, not just the more complex amino acids or the nucleobases. We now, for the first time, have the environment. We have the minerals and the fluids that allow the early steps of the organic evolution towards the first steps of life occurred not in the primordial soup 4 billion years ago on Earth, but in a tepid glass of salty water on an asteroid 4.5 billion years ago. And those asteroids bombarded every solid body in the solar system, from Mercury to Mars to Callisto. They were impacting every solid body in the solar system. They were seeding the ingredients, the fluids, the conditions, the early steps of life. We know those took hold on at least one planet. We call it Earth. Did it on any other planet? And if not, why not? That's the question that remains. So I'm going to leave you with that we found an ancient evaporite mineral sequence in samples of Bennu. This would not have happened without sample return, without careful curation, without state-of-the-art instrumentation, without our staff, and without collections to provide the context, the connective tissue that put this all together. It's the first such sequence from salty, sodium-rich waters outside Earth. But what's really exciting is that those exist today on Earth and today on the icy dwarf planets and moons in the outer solar system. And that these asteroids provided an environment for prebiotic organic formation, both the ingredients and the environment, and these existed at the birth of the solar system and seeded all solid bodies. And I want to end with something particularly for the students. This was an unexpected discovery. This mission came up with dozens of hypotheses before we ever launched, dozens more when we were at the asteroid. This was not one of them. Never did anyone say, we're going to find an evaporite sequence. And so I just want to encourage you, as you go through your professional career, you're going to be asked to do a lot of things. You're going to be asked to write proposals, to write papers, to collect data, to defend things. None of that is why you get out of bed in the morning. None of that is why you do a PhD, okay? I don't get out of bed in the morning to test hypothesis 4.6.3b. I get out of the bed to discover stuff. And you should too. And if you're not getting out of bed every day going, maybe today is the day I get to discover something, then you're really missing out, because that is the fantastic part of what we get to do. We are the true explorers of our age. And I was really fortunate to be part of this, and fortunate to be joined by many of the people in this room, a fantastic group of people around the world to make this possible. This is really our accomplishment, not my accomplishment. Thank you.
Well, thanks, Tim, for a wonderful talk. It was excellent. I know I enjoyed it. I'm sure the rest of you did too. So we'll open up the floor for questions. Questions for Tim. Don't be bashful. Not that I'll ask one, Tim. If you had to design the next mission for sample return, I'm picking your brain. Where would you go? What would you want to bring back?
I'll say the same thing I said in 2011 at the 50th anniversary of the Center for Meteorite Studies at ASU, which is, I think, the next 50 years. We were asked to look at the past 50 years. The next 50 years is the age of ice. And I think it's obvious, ice is it's the most important substance in the solar system. It's the difference between the outer planets and the inner planets. It's what allows life to persist on this planet. It's the source of the water in the early solar system. I mean, ice is really the next breakthrough. And the only thing that keeps us from collecting ice is there's two things. One is the technical difficulty of getting ice and bringing it back to Earth as ice. But there's the equally challenging part of, I think, if we go to all the effort to get ice, if we can bring it back and keep it in that form, we want to be able to study it as a petrologic material, not just a chemical material. If we bring it back and all we do is melt it, then we've wasted the opportunity to really understand it. And that's going to require the development of a whole new set of instruments that are capable of analyzing, liquid nitrogen temperature ices, things like carbon dioxide and even lower temperature ices that we don't have today. I mean, how do you put energy from a TEM into a sample and not melt it, or a nanosims, or anything else? I mean, that is the challenge. And I think if we can overcome those two challenges, that's the obvious choice.
Yeah, Tim?
Yeah, this is a fascinating talk. Great talk, Tim. One of the places people have talked about returning samples is Mars. And I've always said that the best reason is to understand whether life formed there as well. Based on what you're saying here, would you say that if we go to Mars and found life, it would be DNA based, even if it was original?
It's a really good question, whether it be DNA based. I mean, one could envision maybe RNA starting off, but yeah, I mean, that's sort of the logical conclusion. You're forming all the components that lead you down this path towards DNA as this essential building block of life. And, I don't see any reason to think that wouldn't be, and whether that was seeded there. But, these sorts of conditions could not have been rare in the early solar system. We see them today in the outer solar system, but did they occur, on a place like Mars early in the history of the solar system? Especially if you think there were a lot of carbonates. And that's probably the driving thing is, did you have carbonates? The phosphate is going to be the hard thing. But yeah, that would be my guess. So.
Yeah, I mean, we have, there's sheet silicates and these, some of these rocks we think from Mars, they're salts, right?
Oh, yeah.
So you've got the requisite ingredients for
Yeah.
Detaching some of these molecules and maybe making these larger chains. Other
Tom,
questions?
can I ask a question?
Yeah, sorry, I should check online. Yes. Renu? Yeah, go ahead.
Yeah, wonderful talk. Thank you so much. I have two questions. One is there an estimate of the size of the parent body that Bennu came from? And my second question is, you outlined a wonderful series of links from which you deduce this this evaporite sequence. And I'm wondering, what would you say is the weakest link there that you would want to poke at and maybe test this? What are further tests of this whole sequence?
Sure. Really great questions. In terms of the size of the body, I don't think we have a really solid estimate, but I have to think we're looking at something tens or 100 or 200 kilometers across this mud ball that existed in the early history of the solar system. But I don't think we have a good estimate. In terms of what I'd want to poke at, there are a couple of things. I feel really solid about, at least I do, about the relative order of carbonates, and then phosphate, and then the sodium-rich phases. And I think that largely is driven by the fact that you have to remove the calcium to form the magnesium sodium phosphates at all. And then you have to remove the magnesium to ever form the sodium-rich phases. What I'm less confident about is the order of the sodium-rich phases. I wouldn't bet my life because they're all isolated phases. We don't see them in relationship. But I don't think it changes the fundamental story. If you want to rearrange those and you want Williamite before halite or sylvite, or you think that it's, trona came before thenardite, I don't think that really changes the story very much. You might think a little bit about the evaporation sequence. It would be great to see those together. I'm not sure we ever will. But what I really don't know is, where's the ammonia? We see a lot of ammonia in these samples, and there's some discussion that the ammonia is in the magnesium sodium phosphates. But I don't know if it would have taken all of it up, or whether you could have actually formed at the very latest stage of this at very low temperatures, because the water ammonia cotectic is only 175 K, something like that. Whether you could have formed ammonia chlorides or ammonia fluorides, and whether those would even be stable in the conditions that we're keeping the samples in, even in nitrogen. And so I think it's likely that we're going to find more phases. We're going to find more relationships between these phases. But I feel really solid about those three big groupings, less solid about and less concerned about the relative order within them, because I don't think it changes the overall story.
Okay, thank you.
Okay. Yeah, Jess.
Until recently, we thought that salts were pretty rare in the early solar system. And to your point earlier, they don't even discovered in 2 or 3 ordinary chondrites.
Mm-hmm.
What are your thoughts now on potential evaporite sequences also in like the ordinary chondrite parent bodies? And would those also have been places where maybe the sequence could have evolved, albeit in a different way, because they wouldn't have had the clades necessarily?
Yeah, maybe. Yeah. Or you might have gone down, you can look at those, go back to those Hardy and Oyster pathways. You can also follow pathways that lead you to salts that don't take you to the sodium carbonate. They don't take you to Searles Lake. The oceans form lots of salts, and they don't go to Searles Lake because they're not carbonate rich. They're relatively carbonate. So you might have had a completely different system. Without the carbonates that formed in there, without the clays, you might have never gone down this pathway. I think this may be more of an outer solar system, carbonate-rich system where you have a lot of carbonate. And let's not forget, although it's not all carbonate, these rocks have 5% carbon in them. There's a lot of carbonate in these rocks and a lot of carbon in these rocks in general. And so that's probably a driving force on that. But I think maybe if we said, just let me go back a couple slides. One can imagine that you could do it's somewhere here. There. One can imagine you could do this diagram for the solar system, right? This has been done for all the terrestrial systems, but there's lots of pathways that here that take you to, seawater, the Dead Sea, this whole system here takes you down to where, well, that's gypsum crystallization, but there's a variety of pathways over here, and there's more on the other diagram that take you to places where you can envision a whole variety of pathways that, depending on what crystallized, would lead you to different solutions, most of which you can see, and with sodium and chlorine somewhere at the end of that train that never pass through these other systems. I haven't even thought about trying something like that, but it might be an interesting thought experiment to sit down and say, well, how does where would Mars be? Like, what would happen on Mars here versus what would happen on the ordinary chondrites versus what would happen on carbonaceous chondrites? You could probably do a solar system analog for this.
But even in some of the ordinaries, right? Like Samarcona, right? I mean, we find clays and, right?
Yeah. But we don't find a lot of carbonates.
Not carbonates, but we did find there were salts.
Yeah.
So, phosphates,
Yeah. Which is why I'm saying maybe there are other pathways in here, depending on what crystallized leads you one way or another. The phosphates, obviously, if you had a lot of early phosphate crystallization, then you're never going to get to some of these other phases. It's a good graduate student project. It's like a thought experiment for graduate students.
I'm just waiting for Bo to say something about fluid inclusions here.
Have you written this paper yet, Bo?
Have I read it?
No, I mean, written it. The one we were just talking about, that we need this diagram and we need a paper on it. I thought maybe in the last 10 minutes you'd written it.
Any other questions for Tim?
Now that you know of this mineral assemblage from Bennu, would you be looking for the same assemblage or a similar assemblage in other samples, like from moon rocks or other places? Like, especially to test that hypothesis of seeding the entire solar system, right? It would be, I guess, finding the needle in the haystack, but what if you find a grain that looks like this in an Apollo sample?
Yeah, I mean, it is looking for a needle in a haystack, but this whole project has been looking for a needle in a haystack in a field of haystacks. And so, I mean, I think the next, if I were going to spend more time on this project, other than keep going on the Bennu samples, what we really need is to go back to the Ryugu samples. And I think they're starting to do this. So they've recognized the sodium carbonate, they have the magnesium sodium phosphate. But if they see a very similar sequence in the end, they have less samples, and so less opportunity. I told someone I was lucky when I did this, and they said, well, luck is when preparation meets opportunity. We happened to get the right sample. It actually passed through the lab here. Jess sent it to me. Thank you, Jess. And, so we ended up finding this in what passed through to us, because we split that sample up many different ways. But I think I'd like to confirm that it's in another carbonaceous chondrite. If you start to see it universally in these, and then we have the new Awed Chibeka 002. If you're starting to see this now, now you have a trend. Right now we have a data point. If we have a trend, then you can say, well, this is maybe a universal thing of these water, carbon-rich asteroids in the early history of the solar system.
Okay, I think we'll close it out there unless somebody has a burning question, and we'll thank Tim again for a wonderful talk.